Happy to welcome you here to our webinar number 7 on potassium. When is too much, indeed more than we need. I lead the Nutrient Management SPEAR program, which is the college's program that is assigned to helping with the development and implementation and support of science-based guidance for nutrient management in the state of New York. Our motto is to ask ourselves relevant questions and conduct sound science for agriculture profitability, while also focusing on the protection of the environment. We've been in business for the last 25 years and developed a program with 6 focal areas: the land grant, university mission, precision ag, on-farm research, soil health, student engagement. And today we're going to talk a little bit about one of those components, the potassium guidelines for the state of New York. We celebrated our 25th year of existence last August, and that was also the starting point of the development of this webinar series. So far, we've developed 7 webinars started in December last year through the most recent one, which was on June 5th on sulfur management. If you're interested in looking at these webinars, they are now all posted on our YouTube channel within the Department of Animal Science here at Cornell University. So this current webinar will also be posted once we get done with the webinar itself. Our next webinar is going to be on September 4th. We have been trying to do these the first Friday of the month. In August, that's going to be not possible to do, so we're skipping August and we're going into September 4th for the next webinar on soil testing with the title Soil Testing, Morgan, Modified Morgan, Mehlich 3. What? Why? How? Huh? And hope to answer some questions for you related to soil testing. You'll see the screen on the right. That is our list of social media. If you're not signed up for a newsletter, feel free to do so. We have our LinkedIn posts, our website, Facebook, Instagram, X, and our YouTube channel as well. With that, we're going to dive into the webinar for today, potassium. When is too much? Indeed, more than we need. And with that, I also want to introduce Marcus. Marcus is a master student in our program. He's co-presenting with us today. He will also be a lead presenter for the September 4th webinar. I also want to recognize, you see names on the screen here of current and past members of our team that have been actively engaged in potassium work within the Nutrient Management SPEAR program these past couple of decades. The outline for our talk is we're going to start out with a couple of slides on the importance of potassium uptake, deficiency symptoms, soil testing, impact of under and over application, talk a little bit about tissue testing and the utility of forage analysis, potassium levels in forage analysis for making decisions, and then close out with some slides on potassium fertilizers and manure management with potassium as well. And with that, I'm going to hand it over to Marcus.
Thank you, Green. So now let's start with the basics. You may have seen this slide on previous webinars, but it's always important to remember that the plant has 17 essential elements, or in other words, nutrients, which are critical for the plant to complete its cycle. These nutrients are divided into different groups. We have the structural nutrients, carbon, hydrogen, and oxygen. We have the primary and secondary macronutrients, which are required in greater quantities when compared to the micronutrients. For the primary, we have the famous NPK, nitrogen, phosphorus, and potassium, which we're going to talk more today. And for the secondary, we have calcium, magnesium, and sulfur, which we talked on the last webinar. The micronutrients are required in smaller quantities, but they are as important as the macronutrients. We have 8 micronutrients: boron, copper, iron, manganese, zinc, molybdenum, chlorine, and the last element to be classified as a nutrient was nickel. So now let's dive deeper into the potassium concepts. So why potassium is important? Why potassium is considered a plant nutrient? So basically, potassium plays a major role within different metabolic processes inside the plant, such as photosynthesis and carbohydrate transportation from source to sink, which is directly connected to the water management role that the potassium has. The potassium is really important for the stomata opening and closure. I'm going to dive deeper into this stomata function later on the deficiency section. But basically, the potassium needs to get into the guard cells in order to open and close the stomata. And consequently, it's going to influence the transpiration, the water movement, and the nutrient uptake in the plant. The potassium is important for protein synthesis as well, and it can be an important ally against frost damage because the potassium can accumulate inside the cells and reduce the freezing point, helping the plant against frost. The potassium is one of the greatest enzyme activators in the plant as well, and it is highly correlated with stalk strength and diameter for corn. When we are talking about environmental implications, the potassium is not a direct threat to water or air quality, but of course, it can reduce our yields and our nitrogen and phosphorus use efficiency. Moreover, it can reduce our cow performance, especially dry cows, and Corinne is going to talk more about it later. I'm going to hand it over to Corinne again.
So when we start thinking about how to manage potassium, one of the first things to keep in mind is how much is being taken up by common field crops. How many pounds per acre do we remove with harvest? One useful resource here would be to look at the Dairy One feed composition database, where lab analyses are summarized across a certain amount of years in certain areas. In this case, I looked this up for alfalfa hay, so 85% dry matter alfalfa hay, and did a quick calculation that told me that a ton of alfalfa grass hay at 85% dry matter contains about 45 pounds of K2O. You will take the concentration number and then multiply it times 1.2, because in forage analysis, the concentrations are listed in percent K and not percent K2O. So 45 pounds K2O per ton of alfalfa grass hay at 85%. When we look at alfalfa silage and do the same calculation here, with a different number here, silage average listed is 2.8. So about 25 pounds of K2O per ton of alfalfa silage at 35% dry matter. And then the last example we run through here in terms of crop uptake is the one for corn silage. Corn silage, about 9 pounds of K2O per ton of corn silage at 35% dry matter, which also means that if you have a 20-ton crop yield of corn silage, that equates about 170, 180 pounds of K2O per acre. These are clearly book values. You want to do these calculations for individual farms or individual fields, you would need to do the forage analysis for those fields and not rely on book values. But this gives us ballpark figures. We're talking about removal rates in the hundreds. That's why potassium is called a macronutrient. It's taken up in large quantities.
Now, let's go back and talk about the deficiency symptoms. So it is really important to recognize the potassium deficiency symptoms, especially when we are in the field. And for corn and soybeans, as you can see here in the image, the potassium deficiency usually is a yellowing of outer leaves, starting with the older leaves, especially because potassium is a mobile nutrient inside the plant. So when we have a lack of potassium, the older leaves will remobilize the potassium to the younger leaves, and that's why we will see this deficiency with the older leaves. For alfalfa, it is similar. It will also show up with older leaves and around the edges, But for alfalfa, we're going to see some white spots on the edges, while for corn and soybeans, we see fluorosis or a necrosis. And here on this slide, we have two classic symptoms of deficiency. We have the potassium deficiency and the nitrogen deficiency. The potassium deficiency, as I just mentioned, start on the outer part of the leaf, and the necrosis starts from the leaf tip. The nitrogen, on the other hand, the deficiency starts on the inner part of the leaf, and it advances in a V-shaped pattern. And these two deficiencies, they might be quite confusing. They might be, well, similar. So to make it easier to understand, let's focus on the second letter of each nutrient. So the second letter for potassium is O. So O stands for outside. So the deficiency for potassium starts on the outside. Nitrogen, the second letter is I, therefore inside or inner. So the deficiency for nitrogen starts from the inside or inner part of the leaf. It's a really, well, efficient way to remember that. And when we are talking about potassium deficiency symptoms, usually we see the chlorosis and necrosis on the leaf edges, and it's basically because there's a component called putrescine that accumulates on the leaf edges when we have a lack of potassium. Moreover, as I mentioned to you earlier, the potassium is really important for the stomatal opening. So if we don't have potassium, if we have a lack of potassium, the potassium won't get into the guard cell and the stomata won't be able to open and close properly. So it becomes slow to respond, and it may take hours rather than minutes to close. Consequently, the plants become much more susceptible to drought, and the potassium is really important for the plants, not only on normal years, but especially on dry years because of this concept.
So we're going to switch over to talking about soil testing now. We've seen how important potassium is. We've seen sort of ballpark figures for uptake numbers and how to recognize deficiencies once they're there. But it would actually be nice if we identify where we need to apply additional potash before the deficiencies slow up. So we're going to dive into soil testing. Soil testing is the way to know if we have enough potassium for optimum growth. Our standard depth is 8 inches. What we do when we analyze those 8 inches is we try to identify plant available potassium. If you look at the total composition of a soil, there is much more potassium in the soil than we extract in a soil analysis. A lot of our potash is locked up in mineral K, part of the minerals. There's non-exchangeable potassium, there's exchangeable potassium, and solution potassium. Solution potassium tends to be very low. So what we are trying to get at with soil testing is the exchangeable K plus the solution K to get an estimate of, does the soil have enough potassium to supply to our crop, or do we need to apply additional potash? There are 3 approaches that people might think of in terms of making decisions about potash management. The first part listed here is the crop removal approach, where the concept is I calculate how much I remove with my harvest, and I'm going to reapply that back to the ground. Or that's sort of a maintenance approach. A second approach listed here is the sufficiency approach. That is the approach that we tend to go with land-grant universities, where the concept is that we apply if we think there's an insufficient amount of potash and where we could get a yield response, and our recommendations go to 0 once we've reached sufficiency levels. So very much economics driven. Don't apply if you don't need it. Build up on the lower end if there's a deficiency. The K saturation approach is also used by people that make recommendations out in not just in New York, but in other places as well. That's the idea that there is a desired K saturation ratio that we should strive for reaching with our application methods. And Marcus will talk a little bit more about that one. I'm going to dive into the sufficiency approach a little bit more, since that's the basis of how we derive recommendations here and many other land-grant universities. The idea here is that if your soil test is very low, it might be yield limiting. If you apply more potash, you can improve your yield. At some stage, the soil test is so high that we no longer see a response. And that stage is reached. We call that the critical agronomic soil test K level. That means that if you do an analysis for a particular field and your sample comes back and it's less than that critical agronomic soil test K value, that it would be good to add some potash or manure to those fields, because there is a high likelihood of a deficiency and therefore a high likelihood of a response to that extra fertility. If your soil test comes back and it's on the right side of the critical agronomic soil test K value and so higher than that value in this figure, it means we really don't need to apply more potassium. There's sufficient amounts in the soil to reach this optimum yield. When we apply that concept here to New York and we want to derive potassium guidelines, there are three things we need to keep in mind. The first one is to get that best soil sample that we can and to connect that to the local crop response study. So local meaning conducted in New York under New York conditions, in this case for us. We also need to obviously identify what crop we want to grow. But then the third component that comes in is we also need to know what soil types we're dealing with. State of New York has over 600 different soil types, ranging from beach sand to heavy clays. And those 600 plus soil types are organized in 6 soil management groups. Those soil management groups tend to be similar. The soils within each soil management group tend to be similar in texture, origin, and type of parent material, rooting depth, and things like that. Out of those characteristics within a soil management group, it is the soil texture that drives a lot of the potassium supplying capacity. The more clay we have, the greater our potassium supplying ability. And that is because in New York, we have primarily oolitic clays. The example in the middle here within the yellow boundary. So the more clay we have, the more that soil is capable of supplying potassium to the plants. When we see that applied to our landscape, we see that our soils are distributed throughout the state of New York. The southern tier is primarily green. That is soil management group 3. And of course, there are exceptions scattered throughout with our landscape. The lime belt, the red line going from Buffalo to Albany, tends to be the finer textured soils. And you see the distribution throughout the state of New York. One way to get access to that information, to know what your soil management group is for the soil types that you work with, is in the next slide. And that is to go to the database for our soil types. There is a fact sheet that we wrote about soil management groups. If you scan the QR code, you will get access to that particular fact sheet that explains a little bit more what type of soils are in each of these soil management groups. So the way to access that for specific soils is to go to the Cornell soils database. The link is listed here. If you click on that link, you get a database that has the names of all the soils, and this is just the top part of the database. And in the second column, within the darker black lines, is SMG, Soil Management Group. So you can just look up what the soil management group is for your particular soil series, soil type. How do we interpret these numbers now? So in this case, soil test K, we have 5 categories. We go from very low to low, medium, optimum to very high, going from deficient on the left to very high on the right. And then vertically, we have the soil management groups going from 1 through 5, and then 6 is the muck soils. What you see here is an interpretation of the soil test K levels. So if I send a soil sample to the laboratory and the laboratory reported back and said it's 95 pounds of K per acre, I can then look up in this table what that means. If I had a clay soil, it would have meant that it was classified as optimum. If I had a group 4 or 5 or 6 soil, that level of 95 pounds would be classified as low. So it really depends on your soil management group, your soil series, what the interpretation is of the soil test K level, reflecting that the clay soils can supply more potassium than the sandy soils. That also translates in differences in recommendations, where here for the same 95 pound per acre soil test results, our recommendations for the sandier soils are much greater than the recommendations for the clay soils.
So to help interpret these different levels, it is really important to know what is your soil test, because different soil tests or extractants may have different chemical compositions, and consequently the results will be different. So one important step, I would say a key step, is to match your soil test with the test that your local land-grant university recommends. So here for New York, as many of you know, the Morgan test is the test that better correlates with our soils. And it's the one used in the Cornell nutrient guidelines. However, there are many other labs and states around New York that have adopted different tests. For example, some New England states, Massachusetts, Connecticut, they've adopted the modified Morgan test, which has a similar composition to the Morgan test, but it also changes the results. So if we look at this graph here, we have the 1-to-1 line here, what the results would look like if the modified Morgan and the Morgan results were the same. But what we see is that the modified Morgan actually reports more potassium than the Morgan test. The modified Morgan is on the x-axis and the Morgan is on the y-axis. And eventually, the modified Morgan numbers will fall into a different category, into a different soil test K level when compared with the Morgan test. So as you can see here, we have some red lines on the y-axis where you see these differences. So it is really important to match your soil test with your guideline. And many labs across the United States have decided to standardize MELIC 3 as their main soil test. So it's also important to compare MELIC 3 with modified Morgan. So just to pay attention here, now we have switched the axis. So the x-axis is the Morgan K pounds per acre, and the y-axis is the modified Morgan and MELIC 3 potassium amount. So we see again that the modified Morgan reports higher numbers than the Morgan test, and the MELIC 3 also reports higher numbers than the Morgan test, similarly to the modified Morgan. So as we know that the numbers are different and the classifications are different, we need to try to match that with our guidelines or convert these numbers. So for New York, both these tests need to be converted to Morgan equivalents before use in Cornell nutrient guidelines and consequently fertilizer recommendations. And that's what I have been working with. So we are trying to update these equations, not only for potassium, but also for calcium and phosphorus. So far, we have been talking about the soil test potassium levels. But as Corinne mentioned, we also have different approaches to assess our soil potassium status. And one of them is the potassium saturation approach. So before diving deeper into the potassium saturation approach, it is important to remember the cation exchange capacity concept, or CEC. So basically, in easier words, the cation exchange capacity is the amount of space or negative charges available on the soil surface where the cations, especially calcium, magnesium, and potassium, can bind or can be hold. And the potassium saturation is basically the percentage of these spaces occupied by potassium. So the labs to derive the K saturation, they firstly need to estimate the CEC, the cation exchange capacity. And the most common method is the summation method. So basically they extract each individual cation, calcium, magnesium, and potassium using MELIC 3, Morgan, or modify Morgan. And then the sum of calcium, magnesium, and potassium is the CEC. The potassium saturation is calculated dividing the potassium amount by the CEC, or in other words, the potassium amount divided by calcium plus magnesium plus potassium times 100 because it is a percentage. So now we know that there are two different pathways that we can follow, the soil test K and the K saturation. So a question came up many years ago. What's the right pathway? What should I follow to derive my fertilizer recommendations? The potassium saturation or the STK, the soil test potassium? And then the NMSP team at that time, I think 20 years ago, I don't remember, they have conducted a statewide experiment with alfalfa across 15 different fields, applying fertilizer and checking the crop response to this application. And they evaluated which one is the best pathway to follow, the Cornell Morgan soil test, the straight absolute K level in the soil, or the potassium saturation or the potassium ratio in our soil. And as you can see here in this graph, the Cornell Morgan soil test K explained 86% of the variation in the relative yield, while the potassium saturation ratio only explained 26% of the relative yield variation. So for New York soils, for our context, the Cornell Morgan soil test is a better indicator compared to the saturation ratio. And as you can see here, when we have lower potassium saturation ratios, the residual error is greater. And I'll explain to you why. So again, the soil test potassium was a better predictor of potassium needs than the percentage, the K saturation. And the reason why, if you were wondering, is because, as I mentioned, the CEC is calculated by the sum of calcium, magnesium, and potassium. So the labs need to extract each of them individually using MELIC 3 or Morgan. And these tests, most of the times, they are acidic. So for example, the MELIC 3 starting pH is 2.3. And for some soils, especially the New York soils, where we have a lot of glacial soils, we do have a lot of calcium, unavailable calcium. And these tests may overestimate the calcium saturation in the soil. So if you are following the explanation, if we are overestimating the amount of calcium in our soil, we are underestimating the potassium saturation in our soil. And you may think it may lead to high potassium recommendations considerably beyond what the crop really needs. So that's why in our case, in our scenario for our soils, the absolute soil test K is a better tool than the potassium saturation. Another frequent question, especially when the farmer has high soil test potassium levels, is if I have high soil test K, can I have potassium deficiency? And unfortunately, the answer is yes. Because during drought, if you have a dry year, the soil surface will dry and the root activity is going to reduce. And for potassium specifically, it moves in the soil through diffusion, which is one of the three major types of nutrient movements in the soil. The others are mass flow and the physical root interception. And the diffusion is the slowest one, and the most dependent on soil moisture. So consequently, if we have a dry year, a drought, the potassium is not going to move and it's not going to reach the root. Consequently, it's going to decrease the plant uptake. But don't worry, don't worry. Once the soil moisture is restored, the potassium movement to the roots increases again, and the plant uptake increases again. So there's no need to apply more fertilizer. It's not going to increase your yield, because even if you apply more fertilizer, there's no water for the potassium to move. So it's just a matter of weather, and it's gonna be more intense on some specific sites of the field where you have less water and where you have compaction.
And with that, we're going to talk a little bit about the impact of under or over application of potassium. So we've seen what it takes to grow a crop, recognize the deficiency symptoms, learned a little bit about the different soil testing methodologies. Now, what happens if I apply too much or not enough? We did some work in Aurora, New York to evaluate that over a 5-year time span with different potassium levels applied for 4 of those 5 years. And we look at the yield. What we see is in 2006, which was the establishment year of the alfalfa after a corn silage rotation. We didn't have the K treatments there. We implemented them in the beginning, first cutting of 2007. Ended up seeing no differences, no response to potassium. But it was also a drought year. 2008, we had a bumper crop year. It was very high yields at that location. This is 100% dry matter yields. And we saw a little bit of a benefit from rates. The third rate up, 166 pounds, was beginning to yield more than the control. 2009, no differences. 2010, no differences. Altogether, the average yield across each of these treatments was identical, 4 tons of pure dry matter per acre for all K treatments. No yield benefit to K, with the exception of that little bump that we saw in this incredibly high producing year of 2008. So yield didn't increase, but what did increase was with the application of potash, and these are pounds of K2O, not 0060, pounds of K2O. So these are high application rates. With the addition of over 300 pounds of K2O per acre, we see the plant take up more potash. We see the plant K content go up. No impact on yield, but the K content increased, and that results in higher K forages. The other thing we saw when we applied those high application rates was that the soil test K went up. If you follow from the beginning in 2006, where the levels were around 100, 110 or so pounds per acre, the highest application rate, we were in the 240 pound per acre range in the fall of 2010, after those 4 years of those annual applications. So over application resulted definitely in increases in soil test K. The red line is the control. We did not apply any K, and we still harvested that 4 tons of dry matter every year, 4 years in a row from those plots. So we see a downward trend with the mining of soil test K slowly over time. When we take a look at sort of the impact of over under application, we can also start looking at tissue testing or whole plant analysis, which we did with the same study. Here's the potassium content, the percent of K, on the y-axis, and on the x-axis is the soil test. And what we see is that when the soil test goes up, the tissue content goes up as well. That's called basic plant uptake. If it's beyond what the plant needs, it's called luxury consumption. So the plant keeps taking up the potassium as the soil test goes up. For the tips, that would be our traditional tissue analysis. The relationship was a little bit better than for whole plant samples. But for both of those, both the tissue test and the whole plant forage analysis showed the same trend. What we see here too is that the tissue content stayed below 2% across the board, even with these incredibly high K applications that we had in this study. If we then go to traditional interpretation schemes for tissue testing, we often see this number of 2% as the cutoff. We're working with alfalfa here, sampled at early bloom. This chart suggests that the optimum rate is between 2% and 3.5%. These are the top 6 inches, early bloom, top 6 inches of an alfalfa plant. Our field trials did not support that range. It had an optimum potassium content lower than 2%. It suggested that a 2% K cutoff is too high. That it basically results in applications of potash to fields that don't need it. If we look now at tissue testing versus just looking at your forage analysis, we get this line. So on the y-axis is the tissue results, the top 6 inches. On the x-axis is our forage analysis, our whole plant forage analysis. And we see scatter there, but also a trend line, with increasing whole plant values also resulting in increasing tissue samples. And that gives us an opportunity to look at our whole plant analysis, our forage plant analysis, and do an evaluation like, how am I doing with my potash management? So back to the summary on the Dairy One database, taking a look at alfalfa silage in this case, 2.8% K. That would suggest that a lot of our forages, as an average, that a lot of our forages have no lack of potassium. So what you could do, if you're wondering about K management and after the fact evaluation, is take a look at your forage analysis and see if that exceeds the 2%. If that really exceeds 2%, it signals that you're doing totally fine with your K content. You might have more than you needed and might be able to save some dollars the next time around. More is not better. Over application will result in increased K content without increasing yield. And then you have a yield that is higher in K that removes more potash at harvest. So you'll be basically fertilizing for a yield that you then remove with a higher K content that you didn't need, negatively impacting economic returns. Whole plant forage is a key indicator to get a ballpark idea of where you're at with individual fields or at the farm level itself.
Okay, now let's discuss a little bit about the different potassium fertilizers. So you have different options. You may apply manure, especially here in New York and in our region, but eventually you may want to apply some synthetic fertilizers. And the synthetic potassium fertilizers are primarily mined from deposits of potassium. And when we are talking about the major source, potassium chloride or potash, the major mines are in Canada and Russia. And the potassium chloride, the major source, is the most concentrated source. It has 60 to 62% of K2O. But sometimes the farmer doesn't want to apply KCl because of the chloride behavior in the soil, or maybe because the farmer is growing a crop that is sensitive to chloride, although chlorine is a plant nutrient as well. If the farmer wants to use another source, the potassium sulfate is also one of the major sources. It is less concentrated than the KCl. It has 50% of K2O. And it's a little bit more expensive, but it has sulfur as well. So it may be a good source because sulfur is really important for our crops, as we saw in the last webinar. Another minor sources are the Sopomag with 22% of potassium, and it also has sulfur and magnesium. And the less common one is the monopotassium phosphate, which has 40% of potassium, and it also has phosphorus. Now let's talk about manure, which is really common here in our region for our dairy farms. So when we're talking about manure used as a fertilizer, the first thing we need to do is analyze our manure and understand the amount of nutrients that are there. So for potassium, usually when you get your analysis, you're going to see potassium, K, and K2O reported. And basically, because the fertilizers, most of the fertilizers, they are expressed as K2O. It's a chemical consensus. On the other hand, the forage composition, usually the plant's composition, when you send it to an analysis, the potassium is reported as K. So there's a little bit of confusion between K and K2O. And for your manure analysis, you see both of them. So just to make it easier, the conversion is basically 1 pound of K is equal to 1.2 pounds of K2O, and the other way around is also true. So 1 pound of K2O is equal to 0.83 pounds of K. And it is important to remember that the potassium doesn't form structural components in living organisms, and therefore in the manure, it is always in a soluble form, which means it is readily available to the plants. Therefore, the manure potassium can be substituted for the fertilizer potassium on a one-to-one basis. So that's why the K2O is really important. As I mentioned, the fertilizers are going to report K2O. So if you know your manure content, your manure K2O content, you can make this substitution easily. And here we have a table that you can check. It's a fact sheet on the NMSP website, where we have the typical nutrient values for dairy manure in New York State. We have 4 different types of manure: liquid, slurry, semi-solid, and solid. The slurry manure usually has 4 to 10% solids and 90 to 95% of moisture or water. So let's focus on the slurry manure for this exercise. The slurry manure has usually 22 pounds per 1,000 gallons of potassium. And if you are growing an alfalfa, grass, hay crop, usually, as Green said earlier, you have a removal of 45 pounds of K2O per ton. So if you got an yield of 2 tons per acre, you're going to remove 90 pounds of K2O per acre. And if you're going to use this slurry manure, you're going to divide the 22 by 90, and you're going to know that you need 5,000 gallons per acre per year, just to put again the potassium that was removed. If you're gonna get higher yields, up to 6 tons per acre, you may need to apply more manure. It's the same calculation. So you may go up to 12,000 gallons per acre per year. If you don't have the manure analysis, or even if you want to check if your manure analysis is correct, there are new tools available, such as the manure database or manure DB, which was recently released by the University of Minnesota. And they have been collecting different manure samples across the United States from different states and different sources. And they have at least an average of nutrient content across these different sources. So it may be a useful tool as well if you are interested. The website is here on the slide. Here's the fact sheet that I just mentioned with the table for the calculations, the conversions, and also the amount of nutrients in the manure. And this is another important fact sheet, especially nowadays where we have high fertilizer prices. And it's really important to understand what is the value of our manure, what is the actual value of our nitrogen, phosphorus, and potassium, especially if you're a dairy farmer and you want to transfer this manure to a grain crop farm, for example. We have this calculator in this fact sheet. And if we focus here on potassium, K2O first, the first thing you need to have is the nutrient content in this manure. So in this example, we have 21 pounds per 1,000 gallons. You need also to consider the fertilizer price, so the current fertilizer price. Due to, well, a lot of geopolitical things, the prices nowadays are they're going up. So I can ensure to you that it's more than 0.7, but you multiply the nutrient by the price. And also, as we know, as I just told you, the potassium is 100% readily available. So it's times 100%. And you get, in this case, $15 per 1,000 gallons for potassium. And if you want to know more and if you want to play with these calculations, please scan the QR code.
We have a couple more slides left in the presentation. It was mentioned before that if you have more potash available, potassium available and a plant can take up, that the plant needs, it will still take it up. So it results in increased K content in the forages. Potassium can be luxury consumed. That's the terminology we use. And that might have consequences for particular animal groups. High K forages can lead to metabolic problems. And it is in general recommended that, especially for dry cows, we need low K forages, especially during the last 4 weeks of pregnancy. So how do we get those low K forages? One way to do it might be to buy it from somebody else, but if you want to grow it on your own farm, the starting point is to determine how much you need. So how big is your herd? How much acreage do you need to set aside to grow this low K forage? Grow it on fields that test low in potassium, and then avoid all forms of potassium fertilizers on those fields. Even when you do that, you still want to test for K levels in terms of rations to make sure that you actually do have low K forages. There are some differences, species differences and management differences in terms of creating low K forages. The grasses tend to be lower in K than legumes, and there are differences from one grass to another as well. The best options here, reed canary grass, timothy, smooth brome grass, they all tend to have lower K content in their yields than grasses like orchard grass or perennial ryegrass. Two other ways in which you can create lower K forages are to harvest later cuttings for dry K forage, so second, third, fourth cuttings, rather than first cutting. And then also to let the stand grow a little longer than optimal for milk cows, and harvest as more mature grass, because more mature grass will have a higher biomass and a lower K content than the highly nutritious younger grasses. With that, we've reached the wrap up. Just a couple of final statements here for take-home messages. To determine if you need additional potassium, either fertilizer or manure, soil testing is key, but just the soil test is not sufficient. You also need to know the soil management group or the soil series for the field that you're trying to determine a recommendation for. If available, manure can really help with reducing our fertilizer costs. It can satisfy the K needs where needed, depending on how and what rate is being applied. If you want to grow low K forages, watch the way that you do it. Set aside the lowest K fields, no K addition, no manure addition. Select the forages and the management structures to go along with that. Our work throughout the state of New York with our statewide projects and our work in Aurora has shown that tissue K is not all that reliable in making decisions, as the traditional cutoffs of 2% tend to result in recommendations above crop needs. What we do have available for those of us that do forage analysis for rationing, especially for alfalfa there, is the forage analysis samples themselves might give you a hint as to what the situation is. If the alfalfa samples forage K content exceeds 2%, you're very unlikely to have a potassium shortage. And the higher the number, the bigger your opportunities are to lower your K application rates to those fields. So would highly recommend looking at your forage sample once in a while to see how you're doing with your potassium management. Key to all of this, testing is essential to make optimum use of your fertilizer dollars, especially in a time where fertilizers are more expensive and harder to get to. With that, we want to announce once again our fact sheet series. A number of the fact sheets were shared during this presentation. Here's the link, and the QR code gets you to the full list of fact sheets. I also want to share our potassium guidelines document for field crops in New York, and that's a different QR code. This is where we document our guidelines for potassium for field crops in New York, not just corn or alfalfa or soybeans that we talked about here, but for all field crops that we grow in New York. And then last but not least, our thank you to the funding agencies that have allowed us to do these projects and partnered up to actually get the work done. We'll share the next slides, the announcement for the webinar in September. So it's going to be September 4th on soil testing.